All right, we are talking about the regulation inside of the kidney for filtration. So regulation of GFR, glomerular filtration rate regulation through hormones. So we've already talked about autoregulation with myogenic and tubular glomerular feedback, and we've talked about neuroregulation. So now we need to talk about hormones that regulate our glomerular filtration rate. So we need to review some of our hormones. So we talked about the renin, angiotensin, aldosterone system. However, we need to discuss the kidneys and how renin is produced. So when we talk about the afferent arteriole, it's to approach, and the efferent arteriole is to exit. So I just discussed basically that you have a group of cells called the macula densa, which are going to detect amounts of sodium chloride in the distal convoluted tubule. So your distal convoluted tubule is here. Here's your descending limb, your ascending limb, your ascending limb. This is your descending limb of your proximal convoluted tubule, which is going to be attached to the glomerulus. So before we can go through the renin, angiotensin, aldosterone system, we need to review the cells. So afferent arteriole is going to bring it in. The filtrate is going to be pushed into the proximal convoluted tubule. So the filtrate is what's going to constitute the urine. It goes through the proximal convoluted tubule, the descending limb of loop of Henle, ascending limb, and then it's going to go up into the distal convoluted tubule. So we talked about the group of cells that are located right by the efferent arteriole called the macula densa. The macula densa are going to basically be looking for changes in sodium chloride concentration in the proximal convoluted tubule. So this is going to be measuring the amount of sodium chloride in the proximal convoluted tubule, distal convoluted tubule. So we have another group of cells called juxtaglomerular cells. So these cells are going to be right here. Juxta means just next to. Glomerular cells. And these are going to be measuring different things. So whenever we have a decreased GFR, your juxtaglomerular cells, or your blood pressure is low, they're going to stimulate the production of renin. So now we have the name of the cells from the kidney. So the renin, angiotensin, aldosterone system, we need to review this, but when we talk about renin, renin comes from the juxtaglomerular cells of the kidney. So we only produce renin when our kidneys, specifically the juxtaglomerular cells, are going to detect that you have decreased GFR, or we can say decreased blood pressure. When you have decreased GFR, you have decreased blood pressure, your juxtaglomerular cells are going to produce renin. Now, I'm going to use a different paper. This is just like how we reviewed it whenever we talked about renin in the past. So, renin is produced in the kidneys. Whenever we detect there has been a drop in blood pressure, or when we have decreased glomerular filtration rate. So this is the chemical renin that's released from the kidneys into the blood. So renin is going to combine with a plasma protein called angiotensinogen. So, literally, juxtaglomerular cells are going to release renin into the blood whenever it detects that there's low blood pressure or low glomerular filtration rate. Now, renin is going to bind to the plasma protein, angiotensinogen, when they combine, they become angiotensin. Angiotensin 1. So, basically think of renin as an enzyme. Renin is going to bind with angiotensinogen, and when those two bind together, they're like a protein with something bound to it. So we have angiotensin 1, which travels in the blood. So now this is traveling throughout the blood. It travels throughout the lungs. In the lungs, we have an enzyme called ACE, which is angiotensin converting enzyme. This only happens when it travels through the lungs, through the blood, and then it becomes angiotensin 2. Now, angiotensin 2 is going to be a powerful vasoconstrictor. So, we are going to literally say that this is a powerful vasoconstrictor. Since we've been talking about the afferent and efferent arterioles, this one is a powerful vasoconstrictor. So what this one does is it does vasoconstriction of the efferent arteriole. So efferent arteriole is going to be the drain. So literally, we constrict the efferent arteriole of the kidney. Literally, it's a powerful vasoconstrictor of the efferent arteriole of the kidney. Now, when you do that, when you vasoconstrict the efferent arteriole, you're automatically going to increase the amount of GFR. So, this increases the GFR inside of the kidney. So we have more filtrate. Now, keep going. Angiotensin, this is what it does to the kidneys. However, it goes to the adrenal glands, to the zona glomerulosa, and the adrenal glands are going to be stimulated to release aldosterone. Now, aldosterone, we increase our GFR, so we have more filtrate going through the proximal convoluted tubule. But what aldosterone does, let's draw our Bowman's capsule here. And our proximal convoluted tubule, and our descending limb. Okay, so when we talk about aldosterone, aldosterone is going to go to the proximal convoluted tubule, and it tells us that we need to retain fluid. So what happens is over here, we are going to reabsorb sodium back into the kidney, and indirectly on the opposite side, because you reabsorb sodium, you're also therefore going to increase your water. So when you talk about aldosterone, aldosterone is going to reabsorb sodium, and thus you reabsorb water, because water always follows the party. Now, anytime you talk about sodium, you also have to talk about potassium. It's a teeter-totter effect. If you reabsorb sodium, you are going to excrete potassium. That always happens with aldosterone. So you reabsorb sodium, you excrete potassium, but because you reabsorb sodium, you also reabsorb water. So for aldosterone, basically you need to know you reabsorb sodium, you excrete potassium, but the reason you reabsorb water is because you reabsorb water, and water follows the party. So that's your renin, angiotensin, aldosterone system, and we've added a little bit to it. All right, so renin is produced when you have low blood pressure and low GFR. So when you vasoconstrict the efferent arteriole, you can increase the glomerular filtration rate so you can reabsorb sodium and thus reabsorb water to raise your blood pressure. Now, the next one is the atrial natriuretic peptide. So the first system that we had was the renin, angiotensin, aldosterone system. So there's a lot to do with this. The second one is atrial natriuretic peptide, which is going to come from the heart. So your heart is going to detect in the atria that you have an elevated blood pressure. So your atria produces ANP. Now, how ANP works on the kidneys. This is going to basically go to the kidneys. And this is going to help us try to get rid of water. So we need to get rid of water because you have high blood pressure. The goal is to get rid of water. So the way we get rid of water is we need to increase our urine production. We need to increase our filtrate level. So if we need to get rid of water, then we need to increase the GFR, because we can get rid of water, which is going to be urine. Now, I understand that we need to increase the GFR for angiotensin 2, but the only reason we increase the GFR for the renin, angiotensin, aldosterone system is so that we can reabsorb sodium, thus reabsorb water. But on this case, we need to increase the GFR so we have more filtrate. More filtrate means more urine. So this way we can get rid of water. So the way that we can do that on this one is we need to increase our GFR. So we always look at the afferent and efferent arteriole. So if we want to increase our GFR, you need to turn up the faucet. So you would need to vasodilate the afferent arteriole. If you vasodilate the faucet, you have more filtrate, but you're going to vasoconstrict the efferent arteriole, preventing any of that filtrate from exiting. So we can increase the filtrate, we can increase urine, you can get rid of excess water. So atrial natriuretic peptide is going to be produced when you have high blood pressure. So we increase the GFR, you increase the amount of urine, you get rid of water, then your blood pressure is going to drop. So the last one that we have is antidiuretic hormone. which comes from the posterior pituitary. Now, antidiuretic hormone is going to be stored in the posterior pituitary. And basically, whenever we have low water amounts, so the stimulus is you have decreased water content. The posterior pituitary will release antidiuretic hormone into the blood. Now this is also going to go to the kidneys. So we always need to talk about the nephron. So I'm going to draw this out. Guess I can do it this way. Afferent and efferent, my glomerulus. Here's my capsule. Proximal convoluted tubule, descending limb of the loop of Henle. Ascending limb, distal convoluted tubule. Now, ADH, antidiuretic hormone, is basically going to increase the water permeability in the distal convoluted tubule. So, antidiuretic hormone travels in the blood and it goes to the distal convoluted tubule. ADH specifically works on the distal convoluted tubule. Now what it does is it causes your distal convoluted tubule to reabsorb water. When you reabsorb water back to the blood, the stimulus is turned off. So we are going to retain H2O and then we can stop producing antidiuretic hormone. Now, as far as antidiuretic hormone works, there's two things that inhibit the antidiuretic hormone. Caffeine and alcohol are going to inhibit antidiuretic hormone. It literally makes it where you cannot reabsorb water. So that's why when you drink caffeine or alcohol, you pee a lot more. So antidiuretic hormone is stored in the posterior pituitary. The stimulus is you have decreased water. It goes to the distal convoluted tubule of the nephron. You reabsorb water. This therefore is going to increase your water content, and voila, you have a decrease in stimulus. So you stop producing antidiuretic hormone. So to review, hormone regulation, the renin, angiotensin, aldosterone system. The stimulus is the kidneys detect that you have decreased GFR or decreased blood pressure, and that's done by the juxtaglomerular cells. So when you have decreased GFR and decreased blood pressure, you need to increase your water content, which raises your blood pressure. So we want to increase the GFR so that we can reabsorb sodium. And when you reabsorb sodium, then you can reabsorb water, and then your blood pressure is going to go up. Remember that angiotensin 2 is a powerful vasoconstrictor. It's going to vasoconstrict the efferent arteriole. So when you turn off the efferent arteriole, basically you increase your GFR because that's the drain. Okay, atrial natriuretic peptide comes from the heart, specifically from the atria. When you have a lot of blood pressure, your atria overstretches. So the goal is when you have high blood pressure is to get rid of water. So if you have low blood pressure, you need more water. High blood pressure, you need to get rid of water. So we increase the GFR so that we can get rid of urine or get rid of water. So we vasodilate the approaching one. So we turn up the kidneys quite a bit to get rid of water quickly, but we vasoconstrict the efferent arteriole so that it can't drain, so that we can make more urine. The last one, antidiuretic hormone, specifically works on the distal convoluted tubule. When you have decreased water, then you'll produce ADH to retain water to raise it. So that's the hormonal regulation to kidneys in a nutshell. You can read through the PowerPoints, but I am basically just drawing this out because it's a little easier, I think, to draw it out and understand it, opposed to just going through the PowerPoints.